Good day, Math 30-1s. Today we start on a 9.2 lesson talking about analyzing rational functions. Now, last day we learned about questions in this form, which is sort of a standard notation for a transformation of 1 over x. Now, I can look at this one and kind of conveniently say it's shifting 2 to the right, it's shifting 3 up, and there's a vertical stretch by a factor of 2, and I can talk a lot about characteristics from this. It wouldn't be so tough to say the y-intercept is plug in a 0, see what comes out. What's the x-intercept? Plug in a 0 for y, see what comes out. But many of these characteristics are clear considering our understanding of transformations. What changes today is we start to get questions that look a little bit maybe more different. Something like this appears. And we'll be starting to ask questions like, again, what's your vertical asymptote? Are there more than one? Are there no vertical asymptotes? Where's the horizontal asymptote? Is there a horizontal asymptote? Where are your x and y intercepts? And all these questions are sort of implicit in a new understanding today. So, as we begin a conversation about rational functions and the analysis, I have 2 headings in our calculator to examine. Blow your mind 1. First question, what is the domain for x squared minus 4 over x minus 3, and a prediction of maybe what it looks like. So what is the domain? Well, we can kind of focus in on this denominator and say, well, clearly x could not be 3. There's a restriction. So based on my understanding of yesterday, I might think that there's an asymptote at x equals 3. So my guess is that maybe at x equals 3, there's something happening here. And before I try to sketch anything, we'll look at this. We'll see what this looks like in our calculator. But I'm feeling like a quadratic over a line might be kind of unique. So let's shift to the calculator for a moment and see what an x squared minus 4 divided by an x minus 3 looks like. And on a Zoom 6 standard window, we see that, which might look like it's strange. But we actually need to see a little bit further in our window settings. I'm going to see 20 more to the right and 20 more up so we can actually see its true nature, which looks like maybe there is an asymptote at 3, but what's happening in the rest of it? If I were to zoom 3, zoom out, we start to see that it seems to want to appear like a line. But, again, going back in, it wants to be a line, but there's this asymptotic shape that's happening at x equals 3. So it seems like a quadratic over a line is appearing to behave very much like a line. So I'm going to say that it's trying to be a line. It's trying to follow in with that line, but it's kind of curving away and not getting to do that because of this restriction on the bottom. Now, it kind of does make sense that this does want to appear linear because this is a quadratic over a line. And if you think about an x squared divided by an x, you're left with an x. So behaviorally, this is very much like an x. And if you think about it, when you start to plug in values like x equals 100 or x equals 1,000 or x equals 1,000,000 really, really far to the right, eventually 1,000,000 squared and 1,000,000 into this x, that 4 and that 3, they basically appear to have no meaning in the distant future. And so really this is appearing very much like an x with a restriction. So with that in mind, we're seeing sort of this asymptote getting in the way of a line. And so I have one more blow your mind 2 example. What's the domain? Well, again, I can look at this one and say x cannot be a 4. To which you're thinking a quadratic over a line, x cannot be 4. This is probably going to be the exact same visual. To which we slide over and we look at, in brackets, an x squared minus an x minus a 12 dividing by an x minus a 4. And same sort of standard window, first zoom 6, as we see the line starting to appear and then just kept going. Zoom 3, zoom out. Did we miss something? and it still looks like a line. But I thought we said x could not be 4. Well, in fact, second graph in the table, it is still saying that 4 doesn't really work. But what's a little bit unique here, as we zoom back in, is that it wants to be linear, and it's still not going to equal 4, but for some reason, there was no asymptote that was created. And that's where our conversation starts today. So what's actually happening today is this wants to behave like a line, and in fact it will, but there's going to be this, we'll call it point of discontinuity, this hole punch, where the graph exists at 3.9999999 and 4.0000001, but not at 4. So it doesn't exist at x equals 4. That's simply a line not existing at 4. And why does that happen? Well, you might look at this equation very intently and say, well, I know why. There is a top that can factor, and this x squared minus x minus 12 has one of those factors as an x minus 4. So behaviorally, what's actually happening is we've got this x minus 4 on the top that mathematically is getting canceled out with the x minus 4 on the bottom. So mathematically, we're really dealing with x plus 3. This graph is sketching x plus 3, except it's saying I can't do anything at 4. So we could say as an mx plus b 3y intercept and a slope of 1, we could start sketching what this looks like. Rise 1, run across 1, rise 1, run across 1, but I have to be careful because when I get to x equals 4, I have to draw this open circle to indicate this point of discontinuity. So the rest of this graph is going to appear just like this x plus 3, but this point of discontinuity is going to really drive something new today. So this is the first time we're really seeing points of discontinuity, but this happened because there was a factor on the top and the bottom that mathematically canceled each other out. But the remaining part of the function is really what this looks like. So this is what drives today's conversation, that if there is some factor that's on the top and the bottom, it's going to create this point of discontinuity. There's some other scenarios though. If there's a factor that's only in the bottom, it's not going to mathematically cancel out, and it's going to create an asymptote. I should clarify, a vertical asymptote, a restriction of sorts. And if there's a factor that's only in the top, without getting into the math behind it, it will create an x-intercept. So this is when, if you've got a y value that's 0, it's going to create an x-intercept. So the style of question that comes out of this is kind of based on one really, really nice example. 6 equations, 6 graphs, and basically match. So you're very, very welcome to pause this and give it a try. I'm going to comment on the first one, and maybe that's another good place where you can pause and try. But if I factor the very, very top here to say x times x plus 2, and I factor the bottom as a difference of squares, x minus 2, x plus 2, I can mathematically see that this x plus 2 isn't going to have any weight in this. Now that doesn't mean that there is no point of discontinuity. That means because there was a factor on the top and the bottom, there will be a point of discontinuity at x equals negative 2. So down below, I'm going to be looking for a graph with a point of discontinuity at x equals negative 2. But not only that, I've got a factor that's on the bottom, an x minus 2 that's only on the bottom. This creates a vertical asymptote at x equals positive 2. It's kind of like looking for your x-intercepts. You're kind of evaluating that expression to be 0. And on the top, there's an x that is all by itself. And so this is not a binomial. This is an x all by itself. And this is when x is equal to 0. This is your x-intercept. So as you look down below at all these graphs, I'm looking for a point of discontinuity at negative 2. And the only one with a point of discontinuity at negative 2 is graph 2. I also see a vertical asymptote at x equals positive 2. And I see an x-intercept that goes through the origin x equals 0. So I can comfortably say that this graph A matches up with graph 2. And this is the biggest understanding in this lesson, is there's 3 scenarios to remember. I'll kind of finish off this one, and it's worthwhile going through and practicing, but that's the key understanding. So for letter graph B, you have a 2 that can be factored out, and the bottom is not a difference of squares, so it is stuck. There is not a matching top and the bottom, so there's no point of discontinuity. Your graph should not have a point of discontinuity. There is a factor that's only on the bottom, but this one is a little bit unique in that there is no way to make the bottom a 0. There is no restriction. There is no vertical asymptote. So the only thing that's interesting about this graph is there is a factor that's only on the top, so all we should have is an x-intercept at x equals a negative 2. We're looking for no asymptote, no point of discontinuity. So which graph has no asymptote, no point of discontinuity, but only has an x-intercept at negative 2? I'm seeing x-intercept at positive 2, no. Asymptote, 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 asymptote. Maybe it's this one. X-intercept at negative 2 and no asymptote. It is graph 3. Again, for this one, you've got the bottom factors, x minus 2, x plus 2. So we can say there should be 2 factors on the bottom. There should be 2 vertical asymptotes at x equals 2 and negative 2. I can immediately look and say, this should be negative 1 and 2. Nope. Negative 2 and 2. I already know that this is graph 1, but just to confirm, I should see an x-intercept at x equals 0 because there's a factor that's only on the top. X-intercept at 0 because there is a factor that's only on the top. There is no point of discontinuity because there's no matching factor top and bottom, so I don't see a point of discontinuity. So this was graph 1. I'll do one more graph and then I'll kind of continue on, and maybe we'll look at graph M. So graph M factors nicely into an x minus a 3 and an x plus a 3. The bottom has a negative that could be factored out, giving us an x minus a 3. I do see a matching factor top and bottom, which gives us a point of discontinuity at x equals 3. I see a factor that's only on the top, so this gives us an x-intercept at x equals negative 3, and I don't see any factors that are left on the bottom, so there should be no vertical asymptote. So we're looking again for a point of discontinuity at 3 and an x-intercept of negative 3. No asymptote, no asymptote, no asymptote, no asymptote. So this one or this one, I'm seeing no asymptote, point of discontinuity at a 3, x-intercept at x equals negative 3. Let's see. I factored that quite poorly. Thank you. This is a x plus 2, and so our x-intercept should be at x equals negative 2, which again is entirely incorrect. We have this as a factor x minus 2, and this would give us an x equals 2. That was terrible. And so x equals 2 is our x-intercept. This would be a graph 5. So this is the key understanding, that there is 3 scenarios, factors top and bottom, only on the bottom or only on the top, and this gives us a matching. Lastly, as we're getting an equation, we're sometimes given a graph, and so we're going to kind of be asked to take this shape from last day, which seems like we could identify clearly a vertical asymptote and a horizontal asymptote given from our y-axis and our x-axis, just to clarify where those are, that this has shifted 3 to the left, 3 to the left, and it looks like we've traveled 1 up for our asymptote, and that there also appears to be a point of discontinuity. I'm not quite sure what the a value is yet, and I could try to reason through it by talking about shape from where it should be to where it is, but let's cleanly just pick a value that we're very, very confident this goes in, which is a negative 5, 0, and use this location to kind of identify the a value. So I can say that a 0 comes out when a negative 5 gets plugged in. A negative 5 and a 3 makes a negative 2. The negative 1 could subtract over, and we're left with a final answer of a is a 2. So I know that from last day that this is a vertical stretch by a factor of 2. 3 left, 1 up, and here is this shape. But the one thing that I haven't sort of discussed is how do we put this point of discontinuity into the equation? Well, this occurs at a value of x equals negative 1. So there must be a factor of x plus 1 on the top and the bottom of our equation. So somehow we need to introduce this factor on the top and the bottom. Now the problem with this equation is that there's two parts to it. So what I might do is just get a common denominator with this x plus 3 and bring this together as a single fraction, just to make this a little bit more clean. So on the top there's a 2 and an x plus 3. I'll call this an x plus a 5 over our common denominator. Now that I see this simplified expression, we can take this point of discontinuity at x equals negative 1 and introduce the point of discontinuity, x plus 1, x plus 1. So the point of the above common denominator was to simply make a combined expression as one fraction, and this is introducing the point of discontinuity now, which means without it we wouldn't see that hole punch. So we can tidy this up to say x squared plus 6x plus 5 over an x squared plus a 4x plus a 3. And this equation is kind of your simplified expression for this graph. Now there is a little bit of extra understanding that kind of comes from a simplified idea in calculus. And so horizontal asymptotes are something not quite simple. I can look at this graph and see the horizontal asymptote of y equals 1 and look at this equation below and say, I don't see this 1 anywhere in here. I can actually look at this graph initially with the vertical shift up 1 and connect it to this because of a trick in calculus. So if you think about an equation 7x squared minus 10 over 3x minus 6 and two more equations that all look very, very similar, something simple has been changed on each. An x squared over an x squared over an x squared, and an x squared over an x cubed. The only thing that I intentionally changed was the degrees, the powers of each function. So if you imagine for a moment, a horizontal asymptote is really what's happening as you travel really, really far to the right, as you get to very, very large x values. Imagine for a moment, for the top one, if I were to plug in an x value of 1 billion. Eventually, 7 times 1 billion squared, subtracting 10, kind of means that that minus 10 is very meaningless numerically. 3 times 1 billion minus 6, really, that minus 6 is numerically irrelevant. All that really matters is 1 billion squared over 1 billion with a 7 and a 3 hanging out. So really the billion squared becomes so much larger than the billion that there is no horizontal asymptote in this case. The value of this expression just keeps growing. So there is no horizontal asymptote. As long as the degree on the top is larger than the degree on the bottom, regardless of what happens after it, the top is infinitely growing larger than the bottom. This function just keeps growing. It appears almost like quadratic over a line. It's going to appear like a line and just keep growing. Another case. What if this minus 10 minus 6 became again irrelevant numerically as we're growing x squared and an x squared, billion squared, those mean nothing. And in fact, the billion squared and the billion squared kind of cancel out. They behave the same. And so in a way, all that's left as you plug in very, very big numbers is a 7 over 3. So as long as the degree on the top matches the degree on the bottom, what you're going to find is there will be a horizontal asymptote at 2.3 repeated, or 7 over 6. So you would see this graph level off and level off somewhere at 2.3 repeated. And it's simply looking at 7 over 3. Again, at this example above, I could look at this quadratic over a quadratic and say it's a 1 over 1. The horizontal asymptote will be at a 1. I can look back at previous examples and say, where will be the horizontal asymptotes? X squared over x squared, 1 over 1. X over x squared, well, we haven't talked about that case where the bottom is growing faster than the top. We'll look at that in a moment. Same as this one, x squared over x squared, 1 over 1. X over x squared, this is our third example in just a moment, and an x squared over a negative x grows more on the top than the bottom. So this one had no horizontal asymptote. Just to compare it again to graph 5, it did not have a horizontal asymptote. So the last remaining case is, what if the top is growing slower than the bottom? A billion squared over a billion cubed. Eventually, this is going to become 1 divided by infinity. The bottom is growing infinitely larger than the top as x grows to infinity. And eventually 1 divided by the biggest number you could think of is a 0. And so if your bottom has a larger degree than the top, you will have a horizontal asymptote at 0. So your 3 cases are no horizontal asymptote, a horizontal asymptote as the coefficients of your terms with the highest power if they match, and a horizontal asymptote of 0 if your bottom denominator has a higher degree than the top. And this is lesson 9.2, analyzing rational functions.